In digital design, building structural RTL requires the manual declaration and connection of every physical component. When a circuit demands an array of identical primitives, that manual wiring becomes a significant bottleneck. It's visible in ripple carry adders, wide data path multiplexers, or deep shift registers, out 4 separate instantiations of a full adder module, mapping the input and output ports of each one by hand. This code traces directly to the layout, where FA0 passes its carryout to FA1, and so on. At 4 bits, it's manageable, but scale to 64 bits, and the code collapses into 64 discrete module calls and individual interconnect wires. You could abstract this arithmetic into a behavioral block using a simple addition operator. However, hardware engineers often require absolute control over the physical data path, or they are restricted to using specific pre-verified IP blocks for every stage of the adder. Relying on manual instantiation forces a trade-off between structural control and design agility. Hard-coding every connection creates a brittle codebase that cannot easily adapt to changing specifications. Instead of placing each component by hand, the hardware can assemble itself algorithmically based on a set of logical rules. To achieve this, the IEEE 1364-2001 standard introduced a dedicated structural tool, the Verilog Generate block. The Generate construct allows engineers to use procedural programming tools, specifically loops and conditionals, to replicate and route hardware modules algorithmically. This process occurs during the elaboration phase. Before the compiler synthesizes the logic or begins runtime simulation, it evaluates the Generate blocks to map out the exact hierarchy of the circuit. By evaluating these procedural rules before synthesis, Generate blocks provide the scaling power of an algorithm while retaining the precision of gate-level structural design. The primary application of this tool is the Generate for loop. It replicates repetitive structures without requiring the designer to type out each individual instance. In this Verilog snippet for an n-bit adder, the width of the circuit is controlled by a single parameter. Here, size is set to 4. Below that, the Generate for loop wraps the structural logic. During elaboration, the compiler reads this loop and unrolls the hardware. As it iterates, discrete gate instances populate the physical hierarchy, labeled automatically with sequential identifiers like addbit_0.g1 and addbit_1.g1. The loop index defines the gate names, while simultaneously incrementing the array indices for the inputs, outputs, and internal wires. This maps unique interconnecting nets to every specific iteration of the unrolled hardware. Verilog requires a specific syntax to execute this properly. The index variable driving this loop cannot be a standard integer. It must be explicitly declared as a genvar. A genvar is distinct from standard registers or wires. It is a compilation-only variable that exists to evaluate loops during elaboration and vanishes before the final silicon is synthesized. Inside the loop, Verilog automatically generates an implicit local param matching the genvar's name. This allows internal blocks to reference their current index position within the larger hierarchy. The genvar loop operates as a compilation engine, replacing thousands of lines of manual netlist wiring with a single procedural block. Beyond simple replication, Generate blocks enable structural decision-making, allowing a module to select its own internal layout. Using if-generate or case-generate statements, engineers can trigger architectural swaps based on constant expressions evaluated at elaboration. Consider this multiplier code from the IEEE standard. It optimizes its internal structure based on the required bit width of its inputs by using an if-generate statement to check the width parameters. If the passed parameters define a bit width of less than 8, the compiler evaluates the if condition as true, instantiating a carry look-ahead multiplier into the schematic. But if the same module is called with a bit width of 8 or more, the condition fails. The carry look-ahead logic is discarded, and the compiler traces the else path to instantiate a high-performance Wallace tree layout instead. Because this selection happens during elaboration, only the chosen branch translates into physical gates. The unchosen branch is completely ignored by the synthesizer. Since the generation is mutually exclusive, both branches can assign the same instance name without a namespace collision. Conditional generation transforms static IP blocks into reusable modules that adapt their physical architecture to satisfy varying system constraints. System architectures frequently require multi-dimensional arrays, which demand loops nested inside other loops. This introduces a strict rule of hierarchy. Every instantiation of a generate block is treated by the compiler as a completely separate scope. Writing nested B1, B2, and B3 loops makes the compiler build a specific hardware tree. Each iteration creates a deeper branch. Naming each block declares an organized instance array, creating an exact address for every single gate, from B10 down to N3. These hierarchical path names are vital. Top-level modules and verification test benches use these exact addresses to connect wires or probe signals buried inside the generated primitives. If generate blocks are left unnamed, the compiler assigns arbitrary default names, like Gen Block 1. This scrambles the hierarchy, making the design difficult to navigate or debug. Deliberately naming nested generate blocks ensures a predictable schematic, turning abstract, multidimensional loops into organized netlists. Understanding the generate block requires separating it from standard runtime simulation tools, like the always block. The distinction is centered on the difference between dictating signal state and dictating physical existence. An always block governs how data flows through a circuit over time. A generate block executes only once during the elaboration phase to dictate exactly what physical circuits are present on the silicon. While behavioral abstraction handles standard arithmetic, structural generation is required when exact gate-level topologies and verified IP reuse are mandatory. This procedural approach to structure allows modern engineering to scale to massive computational demands without the error-prone process of manual wiring. Mastering the generate construct enables the creation of parameter-driven architecture, where the hardware layout adapts automatically to the shifting constraints of a design.